Welcome to our first video for our flipped class for pre-algebra. For this video, we're going to be discussing the system of real numbers. Alright, so the first thing we need to talk about is what a set is. A set is just a collection of numbers. It can be a collection of anything really, but it's just a collection. That's the key thing. And we can put numbers into our different sets based on their characteristics. For example, if we want to talk about the set of even numbers, well, we know even numbers are just multiples of 2, so that could be like 2, 4, 6, 8, and so on. All right, so that's how we put numbers into a set. And we're going to be talking about these different sets of numbers that make up the real numbers. So here is a graphic organizer to show you how this works. All right, so we have the real numbers. And within the real numbers, we have all of these little subsets. These subsets all have their own defining characteristics. We're going to discuss these. But I want to kind of explain how this graphic organizer works. This is what's called a Venn diagram. And what it shows is that every number that is part of the natural numbers is also part of the whole numbers, and it's also part of the integers, and it's also part of the rational numbers. And everything in here is also part of the real numbers. And then all by itself over here, we've got the irrational numbers. And all together, all of these sets make up the reals. So let's talk about our first subset, and that is the natural numbers. So the natural numbers, those are just the counting numbers. So it's like 1, 2, 3, 4, 5, 6, and so on. All right? It's all the numbers that you learned when you were in elementary school. Just start at 1 and count. All right? And the key thing about these is that they do not include 0. No 0 in the counting numbers. No zeros in the natural numbers. All right, if we are to go one step up from there, we end up at the whole numbers. So all the whole numbers are is it's if we take the counting numbers and we stick a 0 on the end. All right. So the reason this exists, the reason why we have both whole numbers and natural numbers, is that for a long time, like thousands of years, 0 did not exist as a number. And then eventually people decided we needed to have this number 0, and they stuck it on there. And so we got the whole numbers. So that's the key difference. In the natural numbers, we do not have 0. In the whole numbers, we do have 0. And so that's why if we look back at our graphic organizer here, the natural numbers are inside of the whole numbers. Because I could put in here 1, 2, 3, 4, 5, and so on, but no 0 here. But for our whole numbers, we've got 0, and then we've got 1, 2, 3, 4, 5. All right? Everything that's in the natural numbers is also in the whole numbers. Our third set we're going to talk about are the integers. So the integers are all of the whole numbers plus their opposites. All right? They're opposites. So what are the opposites? Well, the opposites are just the negative numbers. So the opposite of 1 is -1. The opposite of 2 is -2. Opposite of 3 is -3. The opposite of 1,245 is -1,245. All right, so the integers include the negatives, which neither the whole numbers nor the natural numbers do. But what we can't have is any decimals or fractions. So we can't have 1/2. Nope, that doesn't work. We can't have 0.75. Nope, that doesn't work. Can't have 1.236. Nope. Only our nice round numbers. So if we go back to that Venn diagram that we have, the integers, well, the integers include everything that's in the whole numbers. So 1, 2, 3, 4, 5. They include 0. But then they also include all the negatives. -1, -2, -3, -4, -5. All right? So you can see that everything that's a natural number is also a whole number, is also an integer. So let's go to our next subset up, the rational numbers. So the rational numbers is any number that can be written as a fraction. All right? So it can be like 1/2, 3/4, 7/5, whatever. Any number that can be written as a fraction. It's any and it can be written as any decimal that either terminates, which just means ends, or ends in a repeating pattern. All right, so let's look at that. 1 is a rational number because I can write 1 as 1 over 1, 2 over 2, 3 over 3, whatever. These all equal 1. Negative 4 is a rational number. Negative 4 is like negative 4 over 1 or negative 12 divided by 3. All right, these fractions both equal negative 4, so it's a rational number. By the same idea, so is 0. 2.35 is a rational number because it ends. It ends. It's 2.35 and then it stops. So that makes it able to be written as a fraction. 7.222222222, on and on and on and on and on forever. We should put this little bar here for repeats. That ends in a repeating pattern. All right? So that also makes it a rational number because it ends in a repeating pattern. By the same idea, so does 4.35353535. It's 35 on and on and on and on and on forever. That's a repeating pattern, so that's a rational number. And then 3/5 is also a rational number. It's a fraction. We can also write that as a decimal. It's 0.6. All right? So these are all rational numbers. So the rational numbers include all of the natural numbers, all of the whole numbers, all of the integers. So we've got like -3, 0, 1, 1200. All right, all of the numbers that fit into these three categories, plus numbers that don't, like 3/7 and 4.8 and 9.6 repeating and 32.9. All right, all of these numbers are rational numbers. So if a number is a natural number, like say 1, it is also a whole number, it is also an integer, and it is also a rational number. All right, so let's talk about our last category, the irrational numbers that are all over here by themselves. All right, irrational numbers are numbers that cannot be written as a fraction. These cannot be expressed as fractions. And they have to have two categories. They have to be both non-terminating, so that means they don't end, and non-repeating, so they don't repeat. So for example, pi. Pi is a really famous number. You should know that it is roughly 3.14159, blah, 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 on and on forever. It never ends. It goes on and on and on, and it never repeats. There's no pattern to the numbers. So by the same example, 3.43257901233330239488, on and on forever. This is also an irrational number because it is both non-repeating and non-terminating. All right? You will find when we get into square roots in our next unit that most square roots are irrational numbers. For example, the square root of 2 is an irrational number. The square root of 3 is an irrational number. All right? These are numbers that both don't end and don't repeat. They have to have both to be part of this. So if we go look at our graphic organizer, you'll notice that if it's in the irrationals, like pi, it cannot be in any of these rational numbers. So if a number is irrational, it's not a natural number, it's not a whole number, it's not an integer, it's not a rational number. It is only irrational. All right? So if you haven't already, I want you to go ahead, pause the video, and copy down this whole graphic organizer so that you have it in your notes. All right, now that you've paused it and written that down, let's look at some examples. So, here's a question. Please pause the video, write down this question before we go through it. All right, so we're going to say name all, and that's key, all of the subsets of real numbers that include -22. All right, so let's go back and let's look at this. Our natural numbers have no negatives in there, so we can't use naturals. Our whole numbers have no negatives in there, so we can't use whole numbers. However, our integers do have the negatives. So negative 22 fits in here with our integers. We can write in negative 22. If it's an integer, it's also a rational number. All right, because the integers are inside of the rationals, if it's an integer, it's a rational number. And then, because of that, the rationals are part of the reals, so it's also a real number. So if I go back to that problem, my answer would be integers, then rational numbers, and real numbers. That is all of the categories, all of the subsets that include negative 22. So, whenever you're doing a problem like this, what you want to do is you want to find the smallest category that they fit into, and then that number will fit into all of the other categories that your smallest category exists in. All right, so let's look at another example. It says, a whole number is also part of what other subsets of real numbers? So, whole number. Well, let's go back and look. If we look at this Venn diagram, we can see that whole numbers are inside of integers, inside of rational numbers, and inside of real. So that means any number that's a whole number is also an integer, is also a rational number, is also a real number. So that would be my answer to that question. I would say integers, rational, and real. Okay? It's the exact same answer as this question. All right, so what we're saying is if a number is a whole number, it is also the integers, rational, and real numbers. We can draw our little Venn diagram here and say, okay, well, in here, put a W for whole numbers. Then out here, whole numbers are all part of the integers. Integers are part of the rational. And then rational numbers are part of the real numbers. Okay, we can draw ourselves a little Venn diagram like that. All right, so let's look at another example. We've got, is the number 2.34534233333 rational or irrational? All right, so for a question like this, or problem like this, we need to ask ourselves two questions. First question is, does it end? Second question is, does it repeat? All right. If either one of these is true, then it's rational. In order for this to be irrational, then both of these have to be false, okay? It has to both not end and not repeat. So if either one of these is true, then it's a rational number. So, question one, does it end? Well, we can see here these ... means it goes on and on and on and on and on and on and on forever. So, does it end? No, does not end. Does it repeat? Well, this first part doesn't really repeat. It's all sorts of weird. But the end, we end up with this repeating pattern of just all threes. Okay? So, I could write another 3 in here, write another 3 in here. It's going to go on forever. I could write a million 3s in here and just keep going. It does repeat. The answer is yes, it does repeat. Well, as I said, if either one of these is a yes, then it is a rational number. So this is a rational number. All right? So I am going to leave you with this try it problem. It says, write all of the subsets of real numbers that 12 over 3 belongs to. So you need to do this problem in your notes and bring it in to be checked tomorrow.